Uh, his research areas are microstrip antenna and UWB antennas, and uh, he has published over 40 research papers in journals. He has also written two books on antennas, uh, and he is also, and I'm proud to say that he is also one of the leading scientists of our time. He is listed on the list of the top 2% scientists of the world in his area. So, welcome, Dr. Sarthak Singhal.
Thank you, sir, for this introduction. So, shall we start?
Yes, you can share your screen and start.
Sir, is my screen visible right now?
Yes, it is visible.
Yeah, so good evening, everyone. Good evening to all the participants, and thank you, Dr. Ravi, sir, for giving me this opportunity for delivering this expert lecture. So, the topic for this presentation is antennas for 5G and 6G applications. Since the title of this FDP is 5G and beyond wireless communication challenges, so one of the major component of any wireless communication system is an antenna. That's why I took this topic for to discuss about the 5G and antennas for 5G and 6G applications. The focus of this presentation will be on terahertz antennas and 6G communication. So the terahertz band is bridging the gap between the micro band, which is from zero point 0.3 to 300 gigahertz, and the infrared region, which starts from 10 terahertz. Okay, so this is the band which is defined for 6G applications. It is having a range of 100 gigahertz to 10 terahertz. It has the features, several features, which I will discuss in the next slide. Okay, this is a promising candidate for the 6G applications, Industry 4.0, medical imaging and sensing applications because of its smaller wavelength, which is quite comparable to the wavelength at the subatomic level, intermolecular separation. So this is a promising candidate for this medical imaging and sensing applications with higher accuracy. The features of this terahertz communications are which makes it a promising candidate are that it's non-ionizing. Okay, it is having a higher penetration with low attenuation inside a wall and all components or whatever devices you are testing. It is having a higher resolution for imaging capacities. Spectroscopic capabilities are there. It will provide a low scattering and high intensity. All are due to this its lower wavelength. Now this terahertz communication is suitable for you can say device to device communication or uh, short range communication because of its lesser band wavelength. The benefits of this terahertz region are the terahertz antennas are they should be directional. They need higher gain because they have a very higher losses Since the frequency is high, so the power losses will be low. Power losses will be high. Okay. It can provide a larger bandwidth, so the channel capacity will be pretty high. Okay, so we can achieve a data rate up to 100 Gbps or up to 1 Tbps. It will be cost effective. Okay, the sizes will be lesser because the size of the antenna should be of the order of half of the wavelength. It is suitable for thermal management also. The problems are with the uh, losses, which is higher in for long range, and one of the major challenges is the fabrication challenge and experimental measurement of at the terahertz frequencies because of non-availability of those sources for the terahertz signals and the sources and the detection devices. Now in this we are talking about the evolution of mobile communication generation. So if we start with the 1G, initially we are able to only transfer the voice signals or the audio signals which are having a data rate of 2.4 kbps only. With 2G and 2G we are able to transmit the uh, voice and text both. Okay, because the data rate was increased with a latency of 300 milliseconds. Then comes the 3G, 4G. So with 3G, we are able to transmit along with the voice and text, we are able to transmit some pictures or multimedia also. Then from the 4G, the mobile internet was also included in the from the mobile devices. Now the 5G is going with 5G is going on, which is talking about the wireless wearable devices and IoT systems or smart cities, so that human error can be reduced and the latency can be reduced and the data can be transferred at a higher data rate, which is in the range of 1 gigabits per second to 10 gigabits per second. And in the upcoming days or the next generation which is going to be evolved or which is supposed to be implemented, its concept is already there, but it is supposed to be implemented in 6G, which will provide the space tourism and the automated cars, because it will have a latency. It requires a latency of only 10 to 100 microseconds. The data rate will be pretty high, that is more than 1 Tbps, 1 terabits per second. So this handling this kind of data rate uh, is quite difficult uh, with the intervention of humans. So the 6G will be the net technology or generation in which the entire communication will be taking place inside the device and between the components. Okay. The different terahertz applications are, as I said, wireless sensor networks, because it is more suitable for this device to device communication. Then the military applications, body area networks, biomedical imaging, ranging and localization, and high speed data links. So the internet speed will also be pretty high. Now, at present, in the across the world, some of the fabrication technologies which are being used for available facility available fabrication technologies which are used for fabrication of these antennas or microstructures or these terahertz antennas are the PCB technology, that is a printed circuit board technology, which will be used only for simple and 2D structures. If we are talking about 3D structure or some complex geometries, then this PCB board technology cannot be used. Then comes your 3D printers or the additive manufacturing technology, which are suitable for uh, fabricating the structural parts of large size and complex shape, and we can achieve a it is suitable for printing or fabricating the 3D geometries also, but only up to a precision of 0.01 millimeter. The problem is with this technology is that there will be surface roughness will be there, which is not acceptable at these terahertz frequencies, so it will be a problem. Okay, then there will be a limited precision and the resolution for higher terahertz frequencies. So getting such a smooth surface, because even if the surface roughness is of very low order, still it can affect the terahertz frequencies spectrum significantly. So in this also, by using this 3D printing or additive manufacturing technology, only a microwave and millimeter wave devices can be fabricated and tested, or we can say up to zero point 0.5 terahertz you can fabricate by using this 3D printing. Okay. The third technology which is available at present is the micro machining or the MEMS technology. This is suitable for 3D micro and nano structures because it allows highly accurate manufacturing of devices, but its cost is pretty high. Okay, and the micro machining tolerance is having a minimum requirement of 1 micrometer. You, so by using this technology, we can uh, uh, design or fabricate the devices which can operate up to only 1 terahertz. If we are discussing about the devices which are supposed to operate beyond 1 terahertz, the this technology will still be not suitable. Now the fourth technology which is supposed considered to be more suitable for the terahertz design fabrication is nanofabrication technology. This allows the manufacturing of elements at the optical frequencies very precisely, but we are talking about the terahertz design, their dimensions are in micrometers. So using the nanofabrication technology, the design dimensions will be pretty high for nanofabrication, but we can achieve that accuracy by using the nanofabrication technology only. So the costing will be pretty high. Okay. So as per the availability of fabrication technologies available in the world, only the MEMS technology and the nanofabrication technology are the two promising candidates for fabrication of this terahertz antennas or devices. So when we talk about wireless communication, see, in case of either we are talking about this 5G up to 4G, the MIMO was suitable, that having a four element at the transmitter and receiver is enough. But when we are talking about 5G and 6G, there is a requirement of massive MIMO antenna element. So the massive MIMO antenna elements requires nearly 100 or more 100 elements at the transmitter side and 100 elements at the receiver side. Whereas in case of 6G, it is assumed or considered that there will be a requirement of around 200 to 400 elements at the transmitter and receiver side both to achieve this latency and this data rate. So when we talk about this wireless communication, there are basic four types of wireless communications. One is your CISO, that is a single input and single output. So in this case, you cannot achieve the diversity, that is, mm, though your path losses and the fading losses cannot be removed. Okay. Then comes your CMO, in which is single input and multiple output. That is, your transmitter will be one, but multiple receivers are receiving. So this is a kind of, we can say, the broadcast system in which one transmitter is transmitting the signal and multiple receivers are receiving that signal. Okay. Then comes your meso, in which only your multiple input and single output, in which multiple transmitters are transmitting the signal and only the single receiver is receiving the signal and identifying which signal I have to receive and uh, reject based on the frequency band. Okay. Then comes your MIMO. So in this, there will be multiple transmitters and multiple receivers. Now, in case of CISO, that is a single input and single output, since the bandwidth will be minimum limited, there will be a constant signal to noise ratio. So the channel capacity will be limited. That is, which defines your overall this channel data rate also. Okay. Now the problem is that with this CISO is multipath propagation. Okay, because if the multipath, if the when the signal travels in free space, it its multiple versions are received at the receiver end. Some are traveling in a line of sight communication manner, and some are coming after multiple diffractions and scatterings. Okay, so this may lead to mm, signal strength weakening at the receiver end. The interference will be larger, and the multipath fading will be there. So as a solution for all of these challenges is a MIMO, that is a multiple input and multiple output. So the major advantages of the MIMO are, as you can see in figure number 5, there are n number of transmitters and m number of receivers. So each transmitter is transmitting the signal to all the receivers. Okay, and each receiver is receiving the signal from all transmitters. That is, there will be total number of signals will be equal to uh, number of transmitters into number of receivers. So the overall channel capacity comes out to be n into m into b, where b is your bandwidth of the single channel, and into log base to 1 plus s by n, that is your SNR, signal to noise ratio. So due to this product of number of transmitter and number of receivers and the bandwidth, the overall channel capacity increases significantly. So from this you can say, in case of 5G, we are talking about hundreds of elements at the transmitter and receiver. So if both the transmitter and receiver are having 100 elements each, so the capacity will increase nearly by 10 to the power 4 times. Okay. And if we are talking about 6G, in which we are talking about 500 elements, so the channel capacity will increase, you can say, 25 into 10 to the power 4 times, which is pretty high. Okay. So the advantage of this MIMO are, you can achieve a better throughput with low bit error rate, because the signal which is traveling in the line of sight communication manner will have a lower attenuation, lower bit error rates. Okay, so you can get better throughput. The signal performance will be pretty high. It supports the full duplex mode, that is, the transmitter and receivers can communicate interchangeably. Okay, both way can communicate, and better spectrum efficiency will be there. The transmission rate, that your data rate is also increasing, network coverage is increasing. Okay, it can support high speed mobile data application. And but the challenge with this MIMO is complex installation and computational complexities due to the signal processing overheads. So these complex installation and computational complexities increases the overall cost of man, initial installation and, or we can say initial implementation and maintenance of the MIMO systems. As I was saying, there are certain specific antenna specifications for 6G applications, which is it should cover the band of maximum bandwidth of 0.1 to 10 terahertz. It should be ultra wideband or multiband antenna. So in case of gigahertz, we talk about the bandwidth an ultra wideband antenna to be having a absolute bandwidth of 500 megahertz, or a particular band of 3.1 to 10.6 gigahertz. But in case of this 6G application, we talk about we call an antenna to be ultra wideband. It is not uh, proven or decided, but it is a concept that an ultra wideband terahertz antenna will be having a minimum bandwidth of uh, 500 gigahertz, and or we can say the spectrum of entire spectrum of 0.1 to we can say of 2 terahertz band. If we are getting it is ultra wideband antenna. Now this ultra wideband antenna will be suitable for low power communication inside the devices over a wide range of frequency. Okay, so which will reduce the chances of signal loss. Now when we are talking about multiband antenna, so in case of this multiband antenna, you can achieve a higher gain, uh, slightly longer range of communication in comparison to the ultra wideband, because it is covering a wide range of frequencies, so the gain will be lesser. So your range of communication will also be lesser. Okay. Now the antennas are classified in terms of radiation patterns also. So if we want to achieve a higher gain for a long range, not very long, but a long range larger than the short range communication, that is between two systems. So which are, then we should it is required to go for directional antennas. Okay, and if we want to communicate uniformly in a overall large over area uniformly, then we would require a omnidirectional antenna. Okay, when we are talking about directional antennas for terahertz, so we should get, for highly directional it should be 25 dBi gain, and if we are talking about omnidirectional, so the gain should be in the range of 18 to 34 dB. Now achieving this kind of gain, either 25 dBi or 18 to 34 dB or 60 dB, will require a large number of elements, that is supermassive MIMOs and array configurations. Then only we can achieve this kind of gain. Okay, the sizes should be pretty less. Okay, the costing should be less, so we it is required that the suitable fabrication technology which is having a lower cost and lesser mm, lower cost should be utilized, but one more challenge is there that the overall complexity of the antenna geometry should also be less. That is, the geometry should be simpler. And one more important parameter or performance aspect for this terrace antenna is that if we are talking about the directional antennas, so they are, we can say, linearly polarized. Okay, but when we want to, if we want to make the overall system to be orientation free, the antenna should be circularly polarized antenna uh, at, at the transmitter also, at the and at the receiver also, so that there should be no signal loss. So in case of MIMO antenna, there are certain performance parameters, which is the isolation should be high so that the individual performance of all the antenna elements or all the elements of the MIMO antenna are not getting affected. Okay, and still we are getting higher data rate and low path losses and fading losses. Envelope correlation coefficients. Okay, then your diversity gain, channel capacity losses. Okay, so this should be lower. Okay, then mean effective gain, the overall effective gain coming out to be. And in case of single element, we talk about the reflection coefficient, but which defines the bandwidth over which the antenna element is operating. But in case of MIMOs, we talk about total active reflection coefficient, which considers the effect of all the elements of that MIMO antenna or this overall array. Okay, it considers the electromagnetic coupling effects due to the nearby elements. Okay. So this envelope correlation coefficient measures the independent. It could be calculated based on S parameters also or far field patterns. As I said, we always want the antenna elements of the MIMO antenna should be highly isolated with each other so that the individual performance is not getting affected. So if the individual performance is not affected, that means their S parameters will be almost the reflection coefficients will be uh, uncorrelated, and the far field patterns will also be uncorrelated. So among these two methodologies for calculating the envelope correlation coefficient, it is preferred to use the far field patterns for ECC determination. Okay. Then comes your diversity gain. It is it defines the multiple versions of so it is all about multi-channel propagation. Okay. So when all the signals are coming to the receiver end, this parameter is being evaluated, and so this is mostly based. It is having a highest value of 10. Okay, and it is dependent on your ECC. So if your ECC is 0, that is the radiation patterns and the S parameters are uncorrelated. So your diversity gain will be 10, and if your ECC is higher, then uh, the acceptable values of the ECC are 0.05. Okay, and the, up to 0.05 or lesser than that, and the so the DG will be nearly should lie between 9.5 to 10 for a good BMO system. Okay. Then comes the channel capacity loss. So this defines the threshold, that is the number of bits per second per hertz, which could be how many bits can be considered to be lost. Maximum limit, it should be lesser than zero point 0.4 bits per second per hertz. Okay, this is a methodology, and this CCL is mostly based on only your S parameters, not on the radiation pattern. Okay. Then total active reflection coefficient, it is the it is considering the parameter. This is the equation for only two port MIMO antenna element antenna. Okay, in the equation we can see that it is considering all the S parameters, that is your reflection coefficient for port 1, uh, transmission coefficient from port 2 to port 1. Okay, and transmission coefficient from port number 1 to 2, and the reflection coefficient of port number 2. So if your torque is 0, then all the delivered power from the source is accepted by the overall antenna, overall MIMO antenna. Okay, and if your torque is 1, then the entire power is reflected back to the source. So in general, as in case of reflection coefficient, we consider the bandwidth to be based on the S11 equal to this minus 10 dB. So similar will be the case for torque. Okay. Now this mean effective gain takes into account the environmental effects. Okay. So how the gain is getting reduced, or this S parameters are getting reduced based on the environmental condition. Now these are the current research areas in the domain of 6G antenna design. So one is low cost, and second one is the designing. And it is desired that an antenna, terahertz antenna which is being designed, it should fulfill both the criteria, that it should be low cost and the design should meet all the specifications in terms of frequency, performance parameters, and in terms of diversity performance parameters. Okay. Now in case of low cost, the cost depends on the fabrication and measurement methodologies. So the measurement is quite difficult because the sources are not available, detectors are not available. So getting the measurement is quite difficult, or right now we can say it is nearly impossible. Okay. And if we talk about the fabrication methodology, so it uh, it is also quite difficult because most of the materials which are existing in the nature or which are developed yet, their frequency and their performance degrades with increasing frequencies. So it may be possible the material which is working well at 50 gigahertz right now, if we say for 5G, it will not work at terahertz frequencies or at the 6G frequency range. So there is a material issue also. Okay, the losses increase significantly. Okay, and second problem is that, so this is was the based on dielectric material, and similarly for the metals start acting as insulators at terahertz frequency. Most of the metals acting as a frequency start acting as a insulators. Okay, so this is one of the challenge with the perspective of material. And in case of technology, the problem is with the frequency band and the antenna shape. If your geometry is complex, you cannot fabricate it. And if your though frequency band is not covered, so there is no use of that fabricated prototype. Okay. So the area of research with respect to this measurement and fabrication is to develop, find new methodologies for fabricating the precise geometries at micro and nano level with high precision and low losses, along with low cost of fabrication. And there is a need of developing the sources, or we can say the transmitter and receiver, which could be used for measuring the antenna performance or the terahertz component performance. Okay. Now, with the perspective of design, one of the issue is materials. Okay, and the second perspective is it should meet all the antenna specification, because we need the polarization also, that is the circular polarization preferable. Okay, even if it is linearly polarized, it is acceptable, but it is preferred to be circularly polarized. The frequency band, because the bandwidth is pretty high, so get covering entire band is a tedious task. Okay, entire bandwidth, then the directivity. So if you want a higher gain, so the bandwidth will be low, and if you want a higher directivity, your bandwidth will be lesser. Okay, the dimension should also be very low, and it should be low cost. Okay, so again, from the perspective of design, there is a need of uh, finding out some materials, developing and new materials and methods of designing the antenna or the tires antenna or tires component, which can fulfill all the design challenges. Okay, some of the materials which are considered to be suitable for this terahertz applications are graphene, uh, and then your this vanadium dioxide, gallium arsenide. Okay, because their conductivity in they are frequency dependent materials, and their losses are less at higher frequencies and nearly constant. Okay, but these materials are not suitable for graphene is not mostly suitable for lower frequency because its conductivity is nearly equal to that of your kind of copper. So fabricate using the copper as a metal conducting metal is um, cheaper than developing the antenna with graphene. Now the first design which I am going to show in this, it is a work done by my MTech student. Okay, it was a dual band notch super wideband MIMO antenna for 5G and 6G application. So this super wideband is a uh, is the term coined for antennas or technology having a ratio bandwidth of 10 is to 1. Okay, we have already discussed the MIMO part. So this was designed, and it was covering up to 3.9 to from 3.9 to 150 gigahertz in terms of simulation, and it was having two band notches. So these two band notches are because of this two slots. One is in the radiator part and second one is in the feed line. Okay, so one is for W line and second one for the X band satellite communication. It was designed on FR4 with metallic part as copper, and by using this element, a gain of 10 dB, a peak gain of 10 dBi was achieved. So this structure started from a simple square monopole antenna with a partial ground plane. rectangular ground plane, and with each step, if we talk about difference between the step number 2 and 3, in case of step 2, the ground planes are symmetric with respect to your antenna element and the feed line, but in case of step 3, we have introduced the asymmetric feeding, that is left part, uh, left half of the leftmost ground plane is edged out. Okay, so in this manner, now there will be two modes which will result into bandwidth enhancement. Okay, so here I am this was having an overall dimension of 18 into 14.25 millimeters. Okay, and this was tested also. Okay, so when we switched from, we are progressing across the designing stages for this antenna, uh, we achieved a bandwidth pretty high from 3.9 to more than 150. Okay, for the initial four stage steps, we got four bands, and thereafter we started getting the two bands. Okay. So this is the comparison between the simulated and the measured result. Due to the availability of measurement facilities only up to 53 gigahertz, we could achieve the measurement for S parameter could be done only up to this. Okay, which is in quite good agreement with the existing, quite a good agreement with the simulated results. Okay, and then this is your input impedance and the gain. As I said, we achieved a gain of nearly 10 dBi near at around 140 gigahertz. Okay, but from this gain plot we can see that at around 40 to 50 gigahertz there is reduction in the gain, whereas till 30-35 gigahertz the measured gain was nearly equal to that of simulated gain. So it is considered that the gain will be may reduce uh, at higher frequencies also due to the substrate losses and the metal losses. So we might achieve a gain of around 7 to 8 dB at 140 or 150 gigahertz. These are the radiation patterns which is in E plane and H plane. So it is seen that at the frequencies of this this will be 45 gigahertz. Okay. So at this for the frequencies of 5 gigahertz, that is lesser than 10 gigahertz, the radiation patterns were omnidirectional in case of H plane. Okay, and in case of E plane, the bidirectional radiation patterns were achieved. Okay, but as the frequency kept on increasing, so the radiation patterns have started uh, achieving distorted radiation patterns, and the overall all the this H plane patterns are nearly omnidirectional, but the E plane patterns are getting significantly distorted. So when we are talking about higher frequency antennas, the radiation patterns will uh, get this directional mostly with high losses. So it is a challenge. It is a challenging task to achieve stability in the radiation patterns or to control the gain this radiation pattern. Okay. Now when this structure was uh, implemented in two-port MIMO configuration in spatial diversity config in which two elements are placed side by side in the parallel configuration and their grounds were connected, and in between a decoupling mm, a decoupling structure was used to reduce the isolation. So in this case, we can see that the S1 and S2 plots are still nearly equal with no effect on the reflection coefficient performance as that of single element, and isolation of more than 20 dB is achieved. Okay, so which signifies that the both the elements are nearly independent. Even their grounds are connected, but their performance are independent of each other. Okay. These are the co and cross pole radiation patterns for E plane and H plane at all these frequencies. So in this we can see that uh, there was a high at certain points the E plane, the cross polarization pattern at 5 gigahertz is lesser than by 20 dB along the broadside direction, but at certain points it is greater than the co-polarized E-plane pattern. Okay, and when we talk about this H-plane pattern, so in H-plane patterns the cross-pole patterns were having a, a difference of nearly 20 dB between the copole and cross-pole patterns. Okay, but as we kept on increasing the frequency, the difference between the levels of co and cross polarization components of E plane and H plane are is getting reduced, and in some cases the E plane cross pole patterns are having higher level than that of this co-polarized pattern. Now, what is the why this decoupling structure was used? See, from figure 16a, you can see at 8 gigahertz when there was no decoupling structure, a large amount of power, a significant amount of power is getting transmitted from port number 1 to port number 2, okay, through surfaces. But as soon as we have introduced a decoupling element, the strength of the signal on the port number 2 due to the excitation of port number 1 is significantly reduced. So at all the frequencies we can see that with the introduction of this decoupling element, the electromagnetic coupling between the two elements is reduced significantly. Okay, these are the ECC DG from the S parameters and from the far field pattern, far field parameter. So in all cases, this ECC was achieved to be lesser than 0.007 for S parameters, and for this far field it was up to 0.04. Okay, and the DG was almost 10 in both the cases. Similarly, for this mean effective gain, we can see that the mean effective gain for both the ports, say either in simulated or measured form, it is lying between -3 to 3.5 dB. Only at these two notches, which are around this one between 4 to 8 and second between 8 to 12, we are getting two dips, and the mean effective gain is reducing to minus 5.5 dB. These are the notched bands. Okay. Similarly, in case of channel capacity loss, in the entire band of operation, the channel capacity loss, that is a number of bits lost per second per hertz, is lesser than zero point 0.4, except those two notched bands where the channel number of bits which are being lost has increased up to 1.6 or more than 1.6 bits per second per hertz. Okay. And another work, uh, hexagonal fractal antenna was designed for super wideband terahertz application, and in this case, a substrate called polyamide was used. So it covered almost entire terahertz band, that is from zero point 0.2 to 11.5 terahertz. Okay, in this three hexagonal rings were used with a partial microstrip line rectangular partial rectangular ground plane, which is loaded with a triangular stub and a square slot with a piece plus shaped slot for generating additional resonances and for improving the impedance matching, resulting into wider bandwidth, along with a pair of is pair of split ring resonator, C-shaped split ring resonator. So in this copper was used as a metallic conductor. Okay, and a peak gain of 10.82 dB was achieved. Okay, it was having a size of 600 to 800 micrometers. Okay. This is a comparison of all the steps which are being followed. So initially for the stage 1, in which a simple hexagonal monopole was designed with a partial ground plane, we achieved this two bands. Sorry, we achieved this four bands. And for the zeroth iteration, that is when the ground plane is partial, a bandwidth of 5 terahertz was achieved. Okay. In case of first iteration, when the hexagonal radiator was loaded with a slot, again the bandwidth has increased because the higher bandage frequency is shifted from 5.56 to 8.17 for the first band, but an additional band was achieved, which is from 8.23 to 11.22 terahertz. Now, when this first iteration was loaded with another ring, then there was a slight reduction in the bandwidth of the first band, and for the second band also, but another band was generated, which is from 10.6. So this second band was subdivided into two bands in case of second iteration. Then we went for this third iteration. So the now in case of third iteration, that is after the introduction of third ring, the lower frequency has shifted significantly to 0.22 from 0.54. Okay, and I think there is some error in this. So at the last, we got a bandwidth of 0.2 to 11.5 terahertz. That is 11.3 terahertz is achieved. These are the VHWR plots for all the design stages. Okay. Now the radiation pattern. So as discussed earlier, at higher frequencies, the radiation patterns are achieve a distorted nature. So it is shown in the figure from these radiation patterns also, that even at one So achieving a stable and constant radiation pattern at this terahertz frequency is a very challenging task. So in this, the gain was achieved up to near the 10.82 dB, and as the frequency was increasing, this efficiency will reduce significantly. Okay, this is due to the substrate and the metal losses. Okay. Then in the another part, uh, any questions? Anyone? Hello. Okay, so in the third work, which is another design of this terahertz antenna. In the previous design, we used the microstrip line feeding technique. Now, in the third design, getting a wide band with CPW feeding, that is by making the ground plane and the feed line on the same plane, coplanar. This bandwidth can be achieved, a wider bandwidth can be achieved significantly with uh, much lesser efforts, but mm, and it reduces the efforts to integrate the antenna with the ICs also. Okay, so we checked that methodology also. So in this, a fractal shape geometry, which is Sierpinski terahertz antenna. Okay, it was used. Sierpinski carpet antenna was used, and with asymmetric feeding. So in this, we achieved a bandwidth of 2.2 to 10.5 terahertz. Again, in this, the substrate was polyamide and the copper was used. This is the ground planes are having their outer edges curved, okay, with slot loadings, okay, and in this you can see the feed line is getting tapered outward also. So what was the why this outward tapering is used? Mm, So in this, from the stage number two, uh, it increased the bandwidth slightly, and the performance was also improved in terms of bandwidth. The major change in the bandwidth took place with this ground slots, okay, and this asymmetric feeding. Okay. These are the radiation patterns. So in this case, due to the fractal geometry and CPW feeding, I guess we achieved the radiation patterns to be stable at 2.3, 2.9 terahertz in E plane and H plane. Whereas in case of as we increase beyond 5 terahertz, the radiation patterns started achieving the omnidirectional nature, and as we move towards 10 terahertz, the radiation patterns got acquired the distorted omnidirectional nature. This is one of the other work in which this is also a circular based terahertz antenna. Okay. These are some other geometries. This is a comparison of the rectangular and circular geometry, which will, from this it can be seen that the rectangular geometries, the circular geometries are providing wider bandwidth in comparison to the circular rectangular geometries. And in these are two other materials, which are silicon can be used as a substrate material and the Teflon can be used, and a combination of these two substrate materials can be used for terahertz frequencies. Okay. Hello, am I audible to everyone? Okay. So at terahertz frequency, uh, initially we took the polyamide material, substrate material, because it is considered to be having lesser losses at higher frequency. Okay, so its performance is supposed considered to be constant at that terahertz frequency, so it was taken. And see, the fabrication technology, as I said, there is no measurement facility available right now for this frequency range, for this terahertz frequency. Okay, but and in case of fabrication, if your geometry is simpler, then you can go for MEMS based fabrication technology. And if your dimensions are very small and geometry complex and you need higher accuracy, so you have to go for nanofabrication. Okay. Now the feeding, if we talk about, see, when you're talking about this feeding, there is a waveguide feeding is preferred, because designing those either microstrip feeding or this coplanar waveguide feeding at that nano scale is a difficult task, but you can design the antenna, okay, and then it could be supported with the waveguides. Now, one more aspect in this is that the feed decision about the feeding depends on your mm, application band, what frequency range you want to target. If you want to achieve a wide band in lesser effects, then you should go for CPW, and it will give you some this advantages in terms of integration with the ICs also. Okay, but if you want to make the line to be balanced, then it should be microstrip feed line. Uh, See, the material losses at the terahertz frequency, uh, because if your conducting material is not conducting, it is acting as an insulator, so your radiation efficiencies will, radiation characteristics will get significantly affected. Okay, so we need to verify whether the conducting material which we are using at the for designing that antenna should have a constant conductivity at those frequencies. Okay, and you can minimize the losses in case of conducting materials by using the frequency dependent materials like your graphene, VO2, gallium arsenide, this now some this Noble materials are there like your nickel, titanium, tungsten, gold, silver. These are the materials which are whose conductivity is constant, and okay, and the graphene, VO2, and gallium arsenide are frequency dependent. So at those terahertz frequencies, their conductivity is constant, whereas at the lower frequency, their conductivity is highly variable. So you can minimize the losses by using these materials. I hope I have clarified the doubts of Pradeep and Rashri. Hello. And one more case is that for the substrate losses, uh, if your substrate losses will increase, so the maximum power will be getting lost from the substrate itself, and resulting into uh, less radiation and impedance, poor impedance matching between the source and the your antenna element or the antenna structure. Okay. So, any other questions right now? Wait 5 minutes. I will be back. Okay, this. So in another work, this earlier we used this square-shaped structure with slots, that is a Sierpinski carpet geometry. Okay. Now this is the Sierpinski antenna in which uh, we have used the circular radiating geometry with the circular slots. So in this case, you can see when we talk about this, compare with this structure, we got a bandwidth of only 2.2 to 10.5 terahertz. Okay, but when we change the geometry to this circular, we achieved a bandwidth of 0.86 to more than 100 terahertz. So the circular geometry is having significant advantages over the rectangular rectangular or the square geometry. In addition to this, there is one more change in this geometry, or we can see the advantage that it is the slots are asymmetrical to the center of the radiator. Along with it, the ground planes are symmetric. Okay, so the geometry complexity is significantly reduced. Okay, and these are the various stages of designing this uh, of deriving this geometry. Okay, and so in this we got a gain of around 12 dB. Okay, and this now when we implemented this in polarization diversity of pattern diversity MIMO configuration, in this we can see the two elements are connected, placed orthogonal to each other, so that one is, so you can see one is the horizontally polarized, the directions of the radiation patterns or the polarizations are orthogonal. Still, as I said, the element should be isolated so that their individual performance should not get affected. So from this figure number 36, you can see the reflection coefficients of both the ports are nearly matching with each other, giving me a bandwidth of 0.86 to 100 terahertz. Okay, with an isolation of nearly 20 dB in the 20 dB or up to 120 dB we have achieved for this geometry. Now the major reason for achieving this larger bandwidth or the lower frequency is the overall dimension, which is 110 by 110 uh, micrometers. Okay, and for this the dimensions were only 42 cross 22. Okay. Now in this, with when we are talking about the circular geometry, the radiation patterns are nearly distorted omnidirectional in nature at all the frequencies, that is from 5.1 to up to 85.1 terahertz. Even we can see that at 25, 45, 65 and 85 terahertz, the radiation patterns are nearly stable in nature of distorted omnidirectional. Whereas in case of 5 terahertz, the at this 90 tera in the first band, that is angular angle of 0 to 180, the beam width was wider, whereas or we can say the pattern was non-directional, whereas along the angle from in the left half of the polar plot we are achieving a nearly kind of directional pattern. Okay, the ECC was in the acceptable limits with the diversity gain of nearly between 9.98 to 10. Okay, the mean effective gain was also nearly minus 3 dB, which is desirable for two port MIMO antenna structures. Okay, the channel capacity loss is also lesser than the acceptable limits of 0.4. Then in another work, it was checked for uh, to use a coach snowflake geometry, which is based on the triangular geometries. Okay, with with symmetric ground planes, but with a curved one. Okay, outer edges are curved with CPW feeding. So in that we got a gain of 11.2 dB. The operating band was from 1.03 to 14.8 terahertz. Okay, so the entire most portion of the terahertz band is covered. Okay, and you can see in the even from the first design step one, in which only a triangular monopole, inverted triangular monopole was designed, two bands are achieved, and in which the first band was already covering the terahertz frequency range. Okay, but as we keep on moving, the lower frequency one and the higher frequency increased up to 14.8 terahertz. Okay. The radiation patterns are also nearly omnidirectional. Okay, in both E plane and H plane. Okay. Now this is the MIMO configuration in spatial diversity configuration, in which the reflection coefficients are nearly matching with each other. Now in this you can see there is certain mismatch around 12 to around 13 to 16 terahertz, This is due to some power loss, uh, coupling, power coupling from port number 1 to 2 or 2 to 1 to the connected ground planes, and very less inter-element spacing. But isolation was very high, that is around 20, more than 22 dB. Okay, but the as reflection coefficients were significantly affected. Okay, so in this we got ECC of lesser than 0.003, diversity gain of nearly 10, and the channel capacity of zero point 0.2 bits per second per hertz in the band of, we can say, 1 to 11 terahertz. And for up to, if we consider the limits of zero point 0.4, then the band is up, CCL is less than 0.4 up to 14 terahertz. Then in another work, this CPW fed Jasmine shaped geometries for you. Okay, so in this the bandwidth was achieved from 0.65 to more than 150 terahertz. Okay. 100 0.65 to 100, more than 100 terahertz. The gain was 11 dB, which was quite comparable with the desired values. Okay, again the dimensions were large, so we got a lower frequency. Even we checked it for FR4 epoxy also, but in the simulation part it is giving a better result, but it is quite doubtful whether it will be practically suitable or not. That can't be uh, claimed right now. Okay, so again, this we got high isolation. Okay, in pattern diversity configuration also, and the envelope correlation coefficient was less than 0.003, diversity gain of nearly 10, and CCL of less than zero point 0.4 bits per second per hertz in the entire band of operation. Okay, so if anyone wants to ask any question right now, oh, is my screen visible now? So I have discussed the few designs. Okay, so yeah, I have discussed this design one. Okay, in which a square shaped Sierpinski carpet was designed. Okay, and a bandwidth of this 2.2 to 10.5 terahertz is achieved. Okay, then we talked about this radiation patterns for the single element, which is stable for up to 5 tera, less than 5 terahertz, but thereafter they started achieving the distorted omnidirectional nature in both the E plane and H plane. Okay, then we talked about the effects of the full and partial ground planes. It was analyzed. So by using the partial ground plane, the bandwidth can be significantly enhanced. Okay, then the two materials were uh, discussed, that is a Teflon and the silicon as the substrate for these terahertz frequencies. Okay, so it is quite visible that when they were compared, the only the single mm, monopoles were compared, the rectangular was giving a better performance, but this performance in general, the performance of the circular antennas are better than the rectangular ones. Okay. Then we talked about, then I have discussed about this circular Sierpinski terahertz antenna in which a bandwidth of 0.86 to 100 terahertz is achieved by increasing the dimensions and using the symmetric ground planes, coplanar waveguide feeding, and asymmetric slot loading of the radiator. Then we talked about the two-port pattern diversity MIMO configuration in which we achieve the entire band of operation as that of single element with an isolation ranging between 20 to 130 dB, 120, 130 dB. Okay. Then the radiation patterns are being discussed in which distorted omnidirectional radiation patterns were achieved at this 25, 45, 65, and 85 terahertz in comparison to slightly directional pattern at 5 terahertz. Then the ECC and diversity gain performance was discussed, which is in the acceptable limits. Okay. Then MEG channel capacity loss. Okay. Then in another task, we talked about the this CPW coach snowflake antenna. Okay, with spatial diversity. So in case of single element, bandwidth of 1 to 14.8 terahertz, that is nearly 14 terahertz band is covered with a peak gain of 11.2 dB. Okay, and the radiation patterns which are distorted omnidirectional. Okay, then their its spatial diversity configuration is talked about. Okay, which is having a isolation of more than 20 dB, 22 dB, but there are certain uh, mismatch between the reflection coefficients of port number 1 and 2 mm, at after 4 terahertz. Okay, then there are diversity performance parameters which are in the acceptable limits. Okay, then a structure of Jasmine shaped was discussed. Okay, which covered a bandwidth of 0.65 to 100 terahertz. So in this FR4 epoxy substrate is highly lossy in comparison to a polyamide. So based on this lossy substrate, this bandwidth is achieved. Okay, but when we are talking, so you can achieve a better impedance matching. Sometimes it would be better or it may degrade. Okay, that depends on the geometry and the substrate material both. And but in practice, achieving this kind of bandwidth with the FR4 epoxy substrate is still not clear whether it will be practically possible or not. Okay. Then the pattern diversity MIMO configuration, okay, we discussed. Then it's diversity performance parameters which are fulfilling the limits. Okay. Now the conclusions of this presentation are that we have discussed about 6 to 7 designs for this 5G and 6G application. The structures were significantly designed and analyzed. So the first challenge of the terahertz antenna, which is designing of antenna to cover the entire band of terahertz spectrum with simpler geometries or less complex geometries is, uh, can be addressed, but the question still remains there that what about the practical conditions? Because right now we can analyze the structures in theoretical and mathematical way, but the practical conditions will be quite difficult, will be different. So there will be higher losses, higher environmental effects on the impedance matching, fabrication issues. Okay. And right now the materials which are being explored in the designs which we have discussed are available in nature, and their properties are tested only up to certain few gigahertz, we can say up to 50 or 60 gigahertz, not beyond that. Or in some cases, they are being uh, explored up to 100 gigahertz. Okay, so what after that, we don't know right now. Okay, and we have designed some structures for discussed with the high gain, that is of the order of 10 dBi and 11 or 12 dBi gains. So the data rates will be pretty high since the bandwidth is high. Okay, but the challenge is it's still there, that how to implement these terahertz in the practical scenario without exploring the material domain. Okay, so there is a high need of designing the materials which can provide stable performance at those terahertz frequencies, and requirement of development of sources uh, and detectors at those terahertz frequencies for making the measurement possible. These are some of the references. Okay, and at MNIT Jaipur we have a anechoic chamber which is available for measurement facilities up to 55 gigahertz. And in my research group, there are certain positions are also open for PhDs and this MTech interns if someone is interested. Okay. And so, is there any question? Uh, yeah, the Teflon may give, as per the availability of literature, this Teflon properties are not known for those terahertz frequencies. That's why I have said that right now the properties which we are checking, or the materials which we are exploring for designing of these terahertz antennas, are based on the properties only up to 100 gigahertz maximum, which are known to us. So the structures which we are designing or exploring right now, they are in terms of simulations and the theoretical studies, but the practical losses and if performance per, we don't know right now. I hope I have answered the question. Hello, any other questions? So I'm concluding my presentation here. If someone wants to ask any question or any query, we can discuss, and can we apply ML model? Yeah, you can apply the ML model for estimating the optimized parameters, but for that you need a larger data set. If you have some data sets available for already existing models, structures with, so you can use the ML models, but it will definitely take the time. It will take larger time than the optimizing the geometries. Yes, you can generate the data set using CST and HFSS or any other simulator, and then you can apply the ML models. But in my personal opinion, and this, it would be better if you go for implementing the inbuilt this optimizing algorithms of, of those softwares. In HFSS and CST, there are certain algorithms already inbuilt in them, which could be used for uh, which are the ML models, and you can use them. So it will require a larger uh, high edge computing infrastructure, because if you are leaving the structure for optimization through those machine learning models or algorithms, it will take a large amount of time and infrastructure, but there will be no understanding kind of thing, or we can say the learning from that perspective. Uh, you can manufacture it through some nano fabrication lab facilities, but testing is TD not possible, I guess. Within India, I don't think the radiation patterns at 210 gigahertz can be measured. Even, but yeah, though measurement facilities for 210 gigahertz are not presently available as per my knowledge. Yeah, the simulation based papers are published, but they need some validation either through two simulators or some theoretical modeling or ECM modeling. Any other questions? Okay. Thank you all for listening me. And if you still have some queries, you can ask, or you can mail me at and mail me at this email ID. For if you have any queries later on, you can ask later on. Thank you, everyone. Thank you.